In our recent videos, we've been discussing the energy model, and we started with the general concept of work. So, just quickly to recap what we've done so far, we started with Newton's laws, did a bit of calculus on it, and we derived the kinetic energy, sort of the energy associated with motion here. This is just one half the mass times the speed squared. So, an useful thing is because the velocity is squared, um, we actually don't have to worry about the direction of the velocity. The energies are scalars, they have no direction. So that can make our lives a lot easier when we're doing these problems or thinking about energy. Um, so we have the kinetic energy there. And the other thing we derived is we defined what's called the work, which, if we think way back to the first time we brought it up, it is the integral from the initial position to the final position of the force dotted with the displacement. These two results here were a direct result of just looking at Newton's second law on a particle and doing some calculus. Then we said, well, if we're looking at a constant force, something we've seen a lot of, so if this force is constant, it can come out of that integral, and then we end up with just the work is equal to the change in kinetic energy of the particle. And this was our work kinetic energy theorem. And that for that constant force, the work ended up being just the dot product of the force with the displacement. So if the force was in the same direction of that displacement, we had a positive work done, that kinetic energy was increasing. If they were in the opposite direction, they had a negative work done, the kinetic energy was decreasing. And the dot products are calculated F dot delta S. We can calculate those just by looking at the magnitude of the force times the magnitude of the displacement times cosine the angle between them. And in the last video, we looked at, well, what if the force isn't constant? We actually introduced something called Hooke's law and looked at the force on a spring, which is right here, and it's equal to negative the spring constant times the how much the spring is stretched or compressed away, how far it is from its equilibrium length. And this is actually useful for not just springs, but elastics, diving boards, essentially anything that has some equilibrium position and it has been displaced away from that position. It's going to want to push back towards the equilibrium position with a force that can be modeled like this. Now, this is a non-constant force, if we think about it, which makes it very hard to deal with using just Newton's laws the way we learned them in the last section of the course. But with work being defined as this integral and us knowing the functional form of that force, we can do that integral, and it turns out we can figure out the work done by a spring. And we went through that last video and ended up being this negative 1/2 the spring constant times, oops, these should be squared, uh, 1/2 k the how far the spring stretched or compressed at the end squared minus 1/2 k how far the springs stretched or compressed at the start squared. Um, and this is kind of a useful thing, and it makes it much, this combined with our work kinetic energy theorem here means we can sort of figure out, okay, how far is this object moving late? How fast is this object moving later? Even though it has this non-constant force acting on it in a much more straightforward way than Newton's laws. Today, we're going to look at a new situation. Today, we're going to think about what's called dissipation. So let's say we have some object that is, let's just say we've given some object some velocity that way, but we're looking at a realistic situation. There's some friction or something here. Eventually, that object is going to stop, right? And why does it stop? Well, obviously because there's some friction between it and the ground. How do we think about this in terms of energy? Is what we're going to look at today. And if we think about that, well, what we have when that object is sliding across the surface is we have the surface of the two objects rubbing together, and we have that frictional force between them where we have this interaction between the molecules of the one object and the molecules of the other. And if you think about more detail about what that's going on is this object at the top is moving relative to the surface on the bottom. It has a lot of kinetic energy when it's moving and all that. Uh, But when these molecules hit, they're interacting with each other, and these molecules are going to, with the one object, are going to interact with the others. They're going to compress and shake these, the bonds between them, and start to get these objects shaking more, these molecules shaking more and more. Those are going to get the ones next to it shaking more. But basically, what we have is this macroscopic kinetic energy, this 1/2 mv squared that we're getting familiar with, all that energy in this macroscopic object. And as it's sliding, we look at the energy of these small atoms or molecules that are making it up. As they interact and slide across each other, they're starting to shake and move more. And they're getting this sort of microscopic energy to it. So they're going to have an increased, each individual atom is going to have an increased kinetic energy. And we're increasing this microscopic energy of the system. After they've hit, they're shaking more. So what's going on here is this macroscopic kinetic energy is sort of being transferred into some microscopic energy. Sorry, I can spell. Microscopic energy. And this is the process, essentially dissipation. When we've been thinking about, our energy model, we have some object we're studying. It's got maybe kinetic, potential energy, whatever. But those are macroscopic energies. We're thinking of, what is the energy of this box, say. Um, there are what's called microscopic energies that we essentially call thermal energy. We chalk all of those microscopic energies and just call it the thermal energy of the system. So the transfer we're looking at when we have these dissipative forces are macroscopic kinetic energy is being transferred into thermal energy, right? And that's because kinetic friction is what we call a dissipative force. It's one of the forces that do this sort of thing. Drag would be another one. When an object goes, really fast through the air, uh, the air molecules are going to start to move faster. Likewise, the hull of, let's say, a spaceship coming back into Earth's atmosphere, the hull of that's going to heat up a lot as it hits those air molecules, and that kinetic energy is getting transferred to that thermal energy. Um, so how do we figure out how much energy is actually transferred? Um, the sort of hand wavy or sort of a straightforward way to think about it that's really useful is you can think about the magnitude of the change in thermal energy as just being sort of the work done by that frictional force. So if we have some situation like this where we have a block that's being pulled by a rope at a constant velocity, um, we have the tension is pulling it that way, doing some work on that object, but we have friction from the surface in the backwards direction. That force is also doing some work, or it's transferring some energy, and that work would just be the force. It's a constant force because it's kinetic friction dotted with that displacement. It is in the opposite direction, so the angle between the velocity this way and the friction that way is 180 degrees. So this ends up being the force dotted with the displacement times or times the displacement. Let's just put those in brackets. Times cosine 180 degrees. So this ends up just being -1, but we have negative the force of kinetic friction, which is mu k times n, times delta x, how far it's moved. That's how we would calculate the work done by friction on this. But if we want to think of how that goes into thermal energy, we're just going to look at the magnitude of that work, and it's going to be equal to the force of kinetic friction times delta x, or just mu kn times delta x. The same thing. So whenever we have some object, uh, whenever we have friction in one of these systems and the object's sliding, that some of that energy, that macroscopic energy, is being converted into thermal energy, and the amount of thermal energy that's being created, or that thermal energy is always going to be increasing in a dissipative situation, is equal to this, the force, the magnitude of the force of friction times the displacement of that. So really quickly, let's work through an example. All right, now here's an example we could solve just using Newton's laws and all that, but it's also, a useful way of solving using kinetic energy. We have a curler who slides an 11 kilogram rock with an initial speed of 2.7 meters per second. Coefficient of friction between the rock and the ice is 0.018. How fast is the rock moving when it gets to the other end of the ice, 15 meters away? Right. So if we want to solve this using energy, essentially we want to figure out how much, what is the energy at the start of this. So initially, there is some energy, kinetic energy, Ki. And at the end, there's going to be some other final kinetic energy, which is essentially what we're trying to figure out. How fast is the rock moving? And this is going to involve how fast it's moving. But because of this friction, there's also going to be some thermal energy there. So all of this energy is just being switched into, some of it's being converted into this change in thermal energy. The rest is remaining in kinetic energy and how fast it's moving. So what we're going to have is 1/2 the mass of the rock times its initial speed squared, its initial kinetic energy, and that's going to be equal to 1/2 mv squared for its final kinetic energy plus the increase in thermal energy, which is just the force of kinetic friction times delta x, right? We've been given all of this information. We've been given enough to figure out that, right? We know the force of kinetic friction is mu k times n. This surface is flat, so if we want to figure out the normal force, we're going to have the force of gravity pulling down, the normal force pulling up, and then we've got this frictional force that way. But in the y direction, we've got the normal force is equal to mg. Those are going to be equal and opposite. So this ends up being mu k times mass times gravity. So we've essentially now got everything we need except for v final. So we can solve this equation. We can do some algebra. We have 1/2 m v initial squared minus mu k mg is equal to 1/2 m v final squared. If we want to do a bit more algebra, we have 2 divided by m, if we bring this over, times 1/2 m v initial squared minus mu k mg is equal to vf squared, or if we take the whole square root of that, it's equal to vf. So that was a lot of algebra in sort of one step, but hopefully we can do that. Knowing our values, right? The mass is 11 kilograms. Vi, the initial speed, is 2.7 meters per second. Mu k is 0.018. Oops, I forgot delta x here. Forgive me. I forgot about that. And the delta x is 15 meters. So if we enter all those numbers in, and just, hopefully we can all use calculators at this point, this ends up being 1.41 meters per second. So again, we could have solved this, using Newton's second law and kinematics and that, but it's useful to see how we can solve it in terms of energy. We're essentially keeping track of where the energy in our system. We start with kinetic energy. That kinetic energy is converted. Some of it's converted into thermal energy because of the dissipative force of friction. Some of it remains as kinetic energy. We know how to calculate those things. So we know the initial kinetic energy. We know how much energy, thermal energy, was created due to that dissipative force. We can solve for the remaining kinetic energy. And that's what we've done. Hopefully this makes sense. We'll be doing a lot of problems like this. There are some subtleties with the energies and the fact that thermal energy, it's not just the ice that's heating up, the rock is also heating up. Both objects have an increase in thermal energy. So, we have to be really careful about how we define our system. We'll discuss that more in future videos and in our synchronous sessions. But yeah, so hopefully this is useful. Bring up questions you have on it in our synchronous sessions, and we'll work more on it there.